why a fan performance table or a fan performance curve is very important in the ventilation design works. Now, let's quickly look at one area where most of the time it's completely taken for granted. Fan performance curve. Now, if you look at this, a simple fan performance curve of a seat, a laboratory fan. I mean, laboratory ventilation. Most of the time they use a seat fan. It's one of the most commonly used in Malaysia, at least, mainly because of its price structure and it's easily available. And somehow or other, the range of the fan easily works for typical laboratory components, the type of hood, which is the heart of a ventilation system. Hood is basically the geometrical shape which are used to effectively capture contaminant at the local point of generation. So now we have a range of materials, a range of components, or this geometrical shape, or are better known as hood in the array of five components of a ventilation system, comprises of laboratory hood, extraction arms, ventilation hood, usually in the forms of canopy or a semi-enclosed hood, semi-enclosed enclosure like booth. Then we also have custom-made hoods like slot hoods, depending on the plane of emission taking place, looking in the working area and what's not. But regardless of that, the hood plays an important role in providing a good capture efficiency, in providing to ensure that it requires small amount of air with highest efficiency. What does this mean? This means that if I use a canopy is huge, a very large opening, and the distance most of the time is away from the emission. For instance, let's assume you have a furnace at a table height of about 1.5 meter, and your canopy is placed at about 2.5 meters. So you have about 1 meter capture distance. This capture distance and the opening of the hood would require a very heavy air. I mean, very high flow rate. Now, so we usually will pick something much smaller, an extraction arm or a slot hood at a very adjacent location, proximity from the emission. Now, that's good. But regardless of all that, at the end of the day, once we complete the hood flow rate calculation, once we complete the static pressure calculation, the selection of the fan plays far more important role. Why? Because most of the time, most of the users or every single stakeholders involved in the project management, the procurement, the decision maker, um, will only look at the capex, capital investment. So because of the capex, everything is done very fast, and most of the time it's time constrained or it's not. One area which is completely overlooked is OPEX. Now, what is capex and OPEX here? Now, look at this fan, array of fans available here. Now, you we have a 730 RPM fan. We have a 930 RPM fan. We have a 1450 RPM fan. We have a 1720 RPM fan. We have 270, 3234. Of course, not all these fans are available in Malaysia, mainly because of the frequency of electrical specification here. But now let's look at the rate fan curves. Yeah, we have fan curves here. Now, when we look at it, it starts with a mere 0.18 up to about, when you look at the 2870 fan curve, it starts with 1.5 kilowatt, 2.2 kilowatt, it goes up to about 3 kilowatt, and what's not. So now assume this. If I now you can actually look at the design point here. The design point, which stands about 660 to 360 kilowatt. This is the design point, right? Assuming that I don't follow this, I just want to pick a big fan. I just want to pick a big fan. Regardless of this, I just want to make sure that I have surplus of air. So I pick this fan, and 2.2 kilowatt, for instance. So I've decided to pick a 2.2 kilowatt fan. Okay. Now what happens here is, you see, obviously the fan is going to be, in actual operation, the fan is going to be churning very high flow rate, but I'm going to use the damper to control it and what's not. So when that happens, my fan operation will be at 2.2 kilowatt at all times. So a 2.2 kilowatt is going to produce a higher amps compared to 0.37 kilowatt fan, motor. A 3.2 kilowatt motor would produce a lower amp compared to uh, 0.37 would definitely incur the amp drawback is much smaller. So what happens here is one wrong selection. In terms of price, it may not vary much. Okay, 0.37 kilowatt fan may cost us about 3,005, just a range, yeah. And then 2.2 kilowatt fan probably will cost us about 5,000. It's just 2,000 different. But what's the major variance here when it comes to OPEX? Your amps are high. That means when the system are running 8 hours a day or 12 hours a day, you are continuously incurring higher costs because we did not give importance in picking the right uh, fan based on the demand. You see, you need a demand of 3 and you give a supply of 10. But the daily effort, the daily energy which takes to give that oversupply is a waste of energy and it's money. And it's money. So that is why it's very, very, very important um, to design a system based on the actual supply and not to oversupply. Now, the other issue here would be picking a 2.2 kilowatt, which where we have a class 3, a fan which runs at 2870 RPM, you are churning a very high noise. It's going to be a very high noise, which is not going to be, which is obviously going to create a noise risk issue. On top of it, you see, again, you're running a very high amps and unnecessarily wasting it on noise generation, high sound generation. So is it really worth it? So think about it. So the next time you install a ventilation system, ensure your system provider put a lot of emphasis to the fan curve. If it is possible, ask them to give you several fans and choose the best option. You see, in terms of the contingency they put in the process, the type or the RPM, and what is the basis of the selection. So this should be one of the most important criteria in as the basis of the overall design.